Two high school students came up with a brand new way of proving the Pythagorean theorem. And today I'm going to help you understand how it works. So we're going to start with a right triangle. I've labeled the angles as alpha and beta. From this, you can see that sine of beta is equal to b over c. We're going to label this as equation 1. Now, we're going to turn this right triangle into an isosceles triangle by reflecting it. Looking at this larger triangle, we can use the sine law. Sine of 2 alpha over 2a is equal to sine of beta over c. Now, remember the first equation? We're going to sub that in for sine beta. When we do that, we'll have sine of 2 alpha over 2a is equal to b over c squared. Now we can isolate for sine of 2 alpha, and when we do that, we'll get sine of 2 alpha is equal to 2ab over c squared. Now guys, here's the cool part. If I can somehow show that sine of 2 alpha is also equal to 2ab over a squared plus b squared, then that would imply that 2ab over c squared is equal to 2ab over a squared plus b squared. And that would prove the Pythagorean theorem, because now our denominators have to be equal. So let me explain how they did that. So guys, we're going to start with the same isosceles triangle. First, we'll extend one of the sides in that manner. Then we'll extend the other side so that it forms a 90-degree angle. Now, since we know that alpha and beta add up to 90, this angle must be alpha. Now, I'm going to create a vertical line to form another right triangle. Now, since this is a right triangle and one of the angles is alpha, then the third angle must be beta. And this means that this right triangle is similar to the right triangles in the isosceles triangle. Now I'm going to create a horizontal line, creating another right triangle. Since that line is 180, well, then again, that means that that angle must be alpha. And the third angle in this new right triangle must be beta. And again, this right triangle is similar to the other right triangles. Now, what we notice is that we can keep on creating right triangles, in fact, infinitely many, and all of these right triangles are similar to each other. Okay guys, now we're going to take a moment to appreciate this amazing shape. It kind of looks like a waffle or an ice cream cone. And the cool thing is that it's composed of two types of triangles. The first one is the isosceles triangle that allowed us to calculate that sine 2 alpha is equal to 2ab over c squared. Secondly, it's composed of a right triangle. Now, this right triangle is going to help us calculate that sine 2 alpha is equal to 2ab over a squared plus b squared. Now, this is going to be crucial in helping us proving the Pythagorean theorem. And in order to do that, our next steps will be to calculate the length of x and y in this right triangle. And it turns out that x is just the sum of all the hypotenuses of the right triangles, infinitely many right triangles on this side. And for y, we can see that it is also the sum of firstly c, which is from the isosceles triangle, and then the hypotenuses of the infinite many right triangles on this side. Now I'm going to label this hypotenuse as x1, the other hypotenuse as y1, and then the vertical line as v1. Now I've enlarged two triangles. We'll label them as A and B. From triangle A, we can see that sine of beta is equal to b over c, sine of alpha is equal to a over c. We'll label them as 1 and 2. From triangle B, we can see that sine of beta is equal to 2a over x1. We'll label this as equation 3. Now if we sub in 1 into 3, we're going to end up with b over c is equal to 2a over x1. And if we isolate for x1, we'll end up with 2ac over b. This is our new equation. We'll label that as 4. The three equations we had are summarized in the top right. Now we're going to use triangle B to solve for v1. We can see that sine of alpha is equal to v1 over x1. v1 is then equal to x1 times sine of alpha. x1 is 2ac over b, and sine of alpha is equal to a over c. And thus, v1 is equal to 2a squared over b. Now we're going to enlarge this triangle and solve for y1. We can see that sine of beta is equal to v1 over y1. y1 is equal to v1 divided by sine beta. v1 is 2a squared over b divided by b over c. Now we'll flip and multiply, and y1 is then equal to 2a squared c over b squared. Now to summarize a little bit, let's go back to our waffle shape. What we did was we calculated that hypotenuse to be 2ac over b. Then we calculated the hypotenuse on the other side as 2a squared c over b squared. And if we had continued using the concept of similar triangle, those would be the lengths that we would calculate. And eventually you'd realize that all of these lengths are multiples of a factor which is a over b. So now that we have discovered that there's a common ratio, to calculate the length of x and y, we can simply use the geometric series. Now basically, guys, x is a sum of all the hypotenuses where the common ratio is going to be a squared over b squared. That's because the hypotenuses were alternating with a ratio of a over b. Now I'm going to factor out 2ac over b and we'll end up with a geometric series. Now because we know the formula, we can replace that part with 1 over 1 minus r. And if we substitute in place of r a squared over b squared and do some algebra, we'll end up with x equaling c over b squared minus a squared times 2ab. Similarly, y is also equal to the sum of all the hypotenuses, except we have to add c at the beginning. Now again, the common ratio is going to be a squared over b squared. It is also a geometric series, so we are going to replace it with the formula 1 over 1 minus r, and in place of r, substitute a squared over b squared. Do some algebra, and we end up with this term for y, which is very similar to x. Now going back to our earlier work, we knew that sine of 2 alpha is equal to 2ab over c squared. Then using the waffle shape, we discovered that sine of 2 alpha is also equal to x over y. Then we calculated our x and y values. Now, if we divide x by y, those two terms will cancel out. And x over y is simply equal to 2ab over a squared plus b squared. This implies that sine of 2 alpha is also equal to 2ab over a squared plus b squared. And if we equate these two, we end up with 2ab over c squared is equal to 2ab over a squared plus b squared. And since our denominators are the same, we have proven the Pythagorean theorem. Guys, I hope you understood all of the steps. If you have any questions, please leave them in the comment section so that I can clear them up for you. The amazing thing about this proof is that it was done by two high school students named Johnson and Jackson. And I hope their work can inspire more students to stay curious and continue doing math, because you never know what you may stumble upon.